dig right in now. I'll go ahead and get started. What I'm going to be talking about today are smart NICs. A smart NIC is a network interface controller with a lot of onboard processing power that allows it to perform some tasks like encryption that improve network and file system I/O throughput. These are the things that connect your T's to the outside world. So if you're persisting data on a file system, on back-end storage servers, you go through the smart NIC. The T's can maintain confidentiality of data and network I/O streams without trusting the smart NIC at all by encrypting the data within the T boundary, obviously. We call this confidential disk encryption, and this uses the CPU in the T and a data encryption key in the T to do all the crypto. And this consumes your CPU cycles inside the T. Now, cloud service providers use hardware and software running on these smart NICs to perform encryption of network and file system I/O. And you see that a lot in general purpose VMs, non-confidential VMs. And when you use these devices, you get significantly increased performance, much higher throughput, because these devices have a lot of processing power and they're designed for CSP infrastructure. This reduces the cost of goods sold, right? It reduces the charge that we have to make for these confidential VMs because these smart NICs are designed and built by CSP, so it's way more economical hardware. And customers who want to use the higher performance can choose to trust these smart NICs to do the encryption, right? You don't have to encrypt data inside the TEE if you're sending data that's not private off through the network, or you're persisting data that's not private on the back end file system storage. You're certainly free to do that, and you get much higher throughput. If you do decide to send private data through this smart NIC, well, CCC requirements state that you have to do remote attestation, as everybody's been discussing in this conference today, using the protocols that are available to do remote attestation of remote devices. That raises the North Star question, which is kind of what I'm trying to dig at in this entire presentation. How do we measure the trustworthiness of a cloud service provider's smart NIC? So that's kind of the outline of my presentation, and now we'll kind of dig into the details. We'll start with that evolution of confidential computing and TCV boundaries. So when things started out, there was an enclave, right? And enclaves were pretty simple. You had a CPU and you had some memory pages that were mapped to this CPU. And all you really needed to do was trust the CPU, because any data that was leaving the enclave was encrypted and being written to main memory. And there were no other devices in the picture. But now, in order to make more workloads compatible with confidential computings, we've got entire VMs with guest operating systems, file systems, and network stacks. And this allows the CPU, and to make these things more flexible, we want the CPU to be able to connect to other devices like these smart NICs in ways that don't violate confidential computing assumptions. So how does this look in a picture? On the right-hand side, we've got a very simplified confidential virtual machine with a guest OS and a CPU. And with confidential disk and network encryption, what we do is we use the in-guest CPU to encrypt and decrypt data as it's being moved from the private memory that's assigned to the confidential VM into shared memory that can be accessed by the device. But the data is already encrypted. So by the time it reaches the device and moves its way into network and storage stack, it's already been encrypted. This is great, but it means encrypting data within the T. What's the downside? Encryption performance overhead. The CPU has to encrypt all the data entering and exiting the T in addition to what it's supposed to be doing. This impacts I/O per second and reduces performance, and can increase cost, because if you want to have more CPU power in order to do the encryption and decryption, you have to buy bigger VMs, and that increases cost. Now, you might say, Why does this matter, right? It's a tough conversation to have. It's tough to talk about this encryption offload overhead. It's easy to measure. We could get a percentage. Why does it matter? If our mission is to safeguard data, we're really not concerned about cost, right? We just want it to be secure. But that's a simplistic view, right? If our mission is to safeguard data, all data, this can only happen if we have widespread adoption of confidential computing. And that can only happen if we reduce friction. Look, I'm not an economist, but I do know from having taken some basic econ classes that if you increase price, demand goes down. I've seen a lot of talks today about how to remove obstacles to the adoption of confidential computing. We can take containerized workloads now and move them straight into confidential computing. Kubernetes workloads can be moved into confidential computing, and that's great that we're reducing those obstacles. But another obstacle that people don't want to talk about is cost and performance. If we don't keep costs in line with GP computing, it's going to lower our adoption and slow the achievement of our mission, which is to secure all data. So what are the alternatives? The alternative is encryption offload. Encryption offload basically says don't encrypt the data within the T, just send it in clear text over to the SmartNIC. The benefits there are pretty clear. You can offload the encryption to the NIC, which has loads of CPU power that's optimized for doing encryption. It frees the host CPU cycles to do its intended workload. The SmartNIC processors, they're free to customers. They're part of the cloud infrastructure. When you buy a VM, you pay for the CPU that's in the VM, but you get all the CPUs that are on the SmartNIC for free. And they're cheaper CPUs, right? They're not the very expensive general purpose CPUs that we're selling in as cloud service providers. So all these things bring down costs, which is a great thing. And in fact, most cloud service providers now are running the control plane on these smart NICs because it's cheaper. And that gives us a powerful incentive to make sure that they're very reliable and they're very secure. But I know what you all are looking at. You're looking at that big red arrow in the middle that says clear text data flow, moving from the confidential virtual machine, the T, into this smart NIC. And you're asking the question, how in the world can I trust that? Why doesn't that violate confidential computing standards? A better way to ask that question is, how much of this smart NIC must be attested? We can see there's a lot there. There's hardware. There's a hardware root of trust, there's firmware, there's an operating system, there's applications. It's basically the same thing that we're trusting inside of RT, that same stack. And at the simplest level, if we trust the smart NIC, what we're asking is that people trust the smart NIC in the same way they trust CPUs. And in order for that to happen, you have to have hardware-based attested isolation of memory from the CSP. So the question is, how do we do attestation? Well, the how is the easiest question to answer, so we'll start there. Attestation is accomplished by using the Security Protocol Data Model, SPDM. This basically creates a secure connection between the T and the attached to the device. It negotiates some data encryption keys so that it can secure traffic over the PCIe bus. This allows the T to query the attached hardware device and get signed attestation reports. So these are things that are being built into processors today and are going to be utilized in the near future, and they give us the ability to do attestation. The other part of the equation is the T device interface security protocol. This allows the T to get configuration data from the hardware device and to enforce the T boundary. So this is the easy part, and these are hardware technologies that allow us to do remote attestation. But the harder question to answer is, what must be attested? And the simple answer is everything inside the trusted compute base. What does that look like in pictures? Well, it's a pretty easy picture. The whole thing needs to be attested. And it's not that different when you think about it from attesting a workload running inside of a container. You attest the hardware measurements, you attest the root of trust measurements, the firmware, and all of those things. Confidential computing requirements, if you look at the CCC definition of confidential computing, it requires a hardware-based, attested, trusted execution environment, which means you have to have a hardware root of trust and remote attestation. All of the hardware that we have inside of SmartNIC could conceivably be attested. We've got the tools to do it. We can attest to all of the items in the stack, the hardware, the programmable logic that's on the silicon, because these are FPGAs. So you basically download all the logic to the chip. The firmware gets downloaded onto the chip. The root of trust is built into a chiplet on the chip. All of these things should be attested, must be attested in order to meet confidential computing standards. But it gets harder because all of these things are independently patchable, right? Other than the silicon and the actual, well, just the silicon in the chip, the rest of these things are independently patchable, and they have to be, because all of these things can have security vulnerabilities. And when the security vulnerabilities are discovered, they have to be fixed, which means new version of the firmware, new version of the programmable logic. And they have to be fixed in ways that have zero downtime. So there can't be any service interruptions. So that means that the SmartNIC is something that is fungible and changing while you're using it without the workload being stopped and restarted. Trust in the verifier. So the attestation of the TCB components just ensures that the hardware and the firmware measurements meet the manufacturer's requirements. And in this case, the manufacturer is the cloud service provider. We all know that that doesn't mean that the TCB is trustworthy. It just means that it meets the manufacturer's requirements. So when you look at the SVN in an attestation report, that attestation verification just proves that the firmware that's running meets the minimum version that's required by the CPU manufacturer. It doesn't prove that it's trustworthy and that it's free of flaws. This protects against important security compromises made by mistake or through malfeasance. For instance, you can use attestation report in a SmartNIC to prove that a node with debugging is enabled isn't ever produced to a production cluster, but it's the cloud service provider that verifies the attestation evidence and makes sure that doesn't happen. It doesn't prove that the cloud provider's work isn't without security vulnerabilities. The way you establish trustworthiness in the attestation verifier is through code publishing, making sure that the code that's running in these SmartNICs is published to a place that can be viewed externally, theoretically by running code audits, and through code transparency. Let's talk about each of those things in a little bit more depth. Code publishing doesn't prove that code is safe, as I just mentioned, but it does allow for the community to inspect code for backdoors and bugs. And if you believe in open source, as do I, you know that eventually open source code, well, not necessarily, or transparent code allows the community to find bugs, to report on bugs, and in the long run, this leads to more secure code. The difference between code transparency and open source is that code transparency allows the manufacturer to place code in a public repository, but you don't necessarily have an open source community that's submitting patches and pull requests that improve the product. This is just allowing a provider of closed source code to share that code with the community. Third-party audits is another way of establishing verifier trust, and we've seen folks do that. Third-party audits basically only provide proof of whatever claims the audit sponsor paid for. Uh, that introduces some interesting conflict of interests because the auditor is often paid for by the provider of the code. Also, it's difficult to keep pace with the production release cadence. As I noted earlier, all of the pieces inside of a SmartNIC are frequently updated, and we can't have an audit done before an important security patch is made available to the public. So another way to approach this is through a code transparency service coupled with a reproducible build system. I'm not going to get into that. That's a several 100-page document, and you could argue about that for a while. But essentially, a code transparency service provides an immutable ledger where production build components and their configurations can be measured, and then those measurements can be registered. And then a reproducible build system allows customers to get equal measurements to make sure that the production build bits that are in the code transparency service are the ones that are actually being deployed. This allows for assurance that the bits that you see in your cloud service provider are the ones that you inspected. All right, so I wanted to come back to my agenda and kind of review it. Cloud service providers offload network and file system I/O to proprietary hardware and software devices, SmartNICs, and the main benefit of this is it increases performance and reduces the cost of goods sold. Ts maintain confidentiality of the file and network I/O stream by encrypting data within the T boundary, but offloading that encryption to these SmartNICs can gain much higher performance while obviously increasing the boundary of the TCB. We can measure this increased TCB using SPDM and TDISP, but that still raises an important question, which is how do we measure the trustworthiness of the CSP's SmartNIC code and hardware so that we can trust them with our confidential data? And that is the end of my presentation.